In this session, we're going to talk about proteins. Now, we introduced biomolecules, and we said some of the examples of biomolecules that we have is we have, we have water, we have proteins themselves, we have, carbs, or let me carbohydrates. Okay, carbohydrates. We have lipids, and all these ones we've talked about them. You can access them on the drive. Then we also have nucleic acids, which we'll talk about in subsequent lectures. Okay, now we're saying proteins are biomolecules. Now you have to understand that proteins are organic compounds. So because they're organic compounds, they are going to be made up of these three elements. They are going to be made up of carbon, hydrogen, and oxygen, and nitrogen. And in some cases, other proteins, they contain sulfur. Okay, sulfur S. Okay, now these proteins are going to be made up from small molecules. Those small molecules that make up proteins, we call them monomers. Okay, monomers. Now when you combine these monomers together, they'll form what we call polymers. Okay, polymers. Now I've introduced two terms, monomers and polymers. So some of the compounds that are going to be made of monomers, example carbs, carbohydrates, have monomers. Okay, for example, an example that you can give is a monosaccharide. A monosaccharide, those are monomers for carbohydrates. Okay, so then another a compound or biomolecule that is made up of monomers is the same proteins that we're talking about. Now proteins, their monomers are called amino acids. Okay, allow me to abbreviate as AA. Okay, then other compounds that are going to have monomers, enzymes will have monomers. Nucleic acids as well. Nucleic acids, they will have monomers as we proceed. Now where am I driving to? I want to tell you that lipids are an exception. Now they are an exception because they are not made of monomers, because they are made up from different distinct molecules. So for carbohydrates, I can give an example. When you're just going to be combining maybe glucose and a lot of glucose molecules, just glucose alone, this will form a certain polymer. Okay, so these that we are combining, they are monomers, okay, of the same compound. But for lipids themselves, they are not going to be made up of monomers. They are going to be mixed with a lot of compounds. Is it glycerol? Is it to make that triglyceride? Because lipids are really different, saturated and unsaturated. And you do well to also watch the video on lipids. So that is very important. So in an exam question that they'll ask you, which of the following is not made up of monomers? So lipids, that's the answer. Now let's talk about something that is very vital, the functions of proteins. Now proteins play a major role in a lot of functions in our body. Okay, they have a lot of functions. Number one that you can talk about is they play a significant role in structure or structural properties. Okay, so they'll be involved in structural properties. A good example that you can give here is collagen. Okay, the collagen is one of those. Another function that of proteins that you can talk about is some proteins are involved in transport. Now transport, an example that I can give, the commonest one that I can give is your hemoglobin, which I'll just abbreviate as HB, and your myoglobin. Now hemoglobin is used for transport of oxygen in blood, okay. Myoglobin is used for transportation of oxygen in muscles, okay. So all these ones are proteins, okay. Then another function of proteins that you need to understand is that proteins will be involved in a lot of enzymes. Let me just call them enzymes. Proteins are enzymes, so because of that they'll be involved in a lot of enzymatic activities, okay. Examples of some proteins which are enzymes, you can talk about maltase. Maltase will just break down maltose to two glucose molecules, okay. You can also talk about sucrase. Now sucrase will break your sucrose like that, okay. So these are some of the enzymes that you can talk about which are proteins, okay, because proteins are enzymes. Proteins are enzymes, yes. Then some proteins they act in the role of hormones, okay. For example, insulin. Now I hope this resonates, because you know about insulin. We've been learning about insulin. So insulin is just one of those hormones that will control or regulate you can talk about your glucose levels in the body. And I must make mention that a hormone is just let me just say a protein substance that control or regulate body activities. And I've just said insulin we know control your blood glucose levels. If they are high, your glucose will be converted to glycogen. When it's converted to glycogen, it's going to be stored in the liver. Then there's another hormone, glucagon. In case you have less glucose in your body, the stored glucose that was stored in form of glycogen will be broken down so that your body can use depending on the activity that you're doing, okay. So you must understand that. Then another key function of proteins that you need to understand is these proteins are used, some proteins are used for protection. A common example of protection, we're talking about antibodies, immunoglobulins. That's the other name, okay. So antibodies, so they'll fight foreign substances which affect your body, or that may pose a danger to your body. So you must understand these. And proteins have other roles. This list is not exhaustive, okay. Now let's talk about something else. We said proteins, they are made up of monomers, and monomers, these are just the simplest unit of a biomolecule, okay. So proteins, we said they are made of monomers called amino acids, okay. So these ones are the basic building blocks of proteins. So basic building blocks of proteins. So now, if amino acids are the basic building blocks of proteins, let's look at the basic structure, just the basic structure of an amino acid. So just the name itself, we've got an amino, meaning we have an amino group, right? Then we have an acid. So in this case, you're going to see as we draw the structure. So it's a combination of an amino group and an acid. So let's say there's carbon here, it's on the middle, okay. Then there's C, and like this. So this side you have you know, a carboxylic acid. On the other side you have an amino group. Okay, so this with me here is, this is a basic structure of an amino acid. Now you're able to see that the carbon at the center, okay, the carbon at the center is connected to 4 groups. Okay, there is this one, there is that one, this one, and that one. Okay, so now if these groups are different, you remember we've been talking about what? Chirality, or a chiral. It will be called a chirocarbon. And what happens with chirocarbons, you know, they tend to produce what we call you know, enantiomers or stereoisomers, mirror images of a compound, because they tend to rotate plane polarized light in a certain direction. What does that mean? If it's a chiral compound, let's say this is our protein, and this protein is connected to 4 different groups. If we take light, we pass this light through this protein. This, let me say this is light, okay, from a light source. If it hits through this protein, if that protein has a chirocarbon, that light will be rotated. It will either be rotated to the right, let me say this is my right, and either to the left. Okay, when it is rotated to the left, it will be called levorotatory, you know, motion or rotation. Then when it's rotated to the right, it will be called the dextro-rotatory. Okay, you must also understand that concept, very, very important. Okay, then I must make mention something that is very critical here. So what are the names of these groups? Okay, so earlier I've said this group is called the carboxylic, you know, acid. A carboxylic acid or carboxylic you know, functional group. So others will call it a carboxyl. In other books they'll call it a carboxyl group. Okay, so because of this group, that's why we call these, you know, basic building of blocks of, you know, proteins as amino acids. Why? Because they've got an acid. Okay, then on the other side, this group is what we are calling an amino group. Okay, an amino group. Then the H here, this is just a hydrogen. Our R in this case, this is called an alkyl group. Now an alkyl group, you have to understand here. So this alkyl group, okay, so alkyl, this is a spelling. So alkyl group, so this alkyl group, it will be very different from all the proteins that we're going to talk about. Okay, and this is what determines the function of that amino acid, because of the difference in the you know, the R group. Okay, so the difference in the R group would determine the kind of the amino acid and its properties. Okay, so this is how we write the structure for you know, a protein or a basic structure for an amino acid. Then you might also want to write it in another form. Okay, so another way of writing this structure is just, you know, in a straight form. Okay, a straight chain where just say H2N, this is connected to, then you have your carboxyl group, you have your R group, and you have your hydrogen there. Okay, so this is another way you can write the structure. Okay, now these amino acids, what are they, and which ones are we going to focus on? So there are about 20 amino acids that are available. Okay, 20 amino acids that are available. Okay, and the simplest of these ones is what we call glycine or glycine. Okay, glycine will be the simplest of all of them. Now this one you must know because it's the simplest. Okay, so So glycine, the structure of glycine is just a simple one. So if a compound, let's say this, you've got your COOH, you've got your H, you've got your H2N. For glycine, because it's the simplest, here on the R group, we said proteins, the amino acids differ at the R group. Glycine will have an H here. Now, is it achiral or is it chiral? Is it symmetric or asymmetric? Okay, so in this case, glycine is achiral. Okay, achiral, or let me say it is symmetric. So symmetric to mean it doesn't have a chiral carbon. How? Because it has yes, it has different groups, but not from all the groups are not like, we've got two groups which are the same. Okay, so these two are different, but you've got an H here and you've got an H, so it's an achiral molecule. So what are we talking about? Glycine cannot, it is optically inactive. It cannot, rotate plane polarized light. Okay, meaning, what does it mean? If this is your glycine, you get your light, you pass through this glycine. This light will not be rotated anywhere. It will just be passing through glycine. Okay, it will just be passing through as if there is nothing. Why? Because it doesn't have a chiral carbon. Okay, now most of the amino acids that are found, because we were talking about, chiral, we've introduced the aspect of chirality. We're talking about, this chiral carbon tends to each, rotating light either to the left or to the right. Okay, now most of the amino acids that you are going to find are going to be found in the L form. Okay, now you must understand, you must know this one, in the L form. Okay, on the contrary, we said like carbohydrates, for them, most of them are found what? In the D form, right? For carbs, it's in the D form, but for proteins, okay, for proteins it will be in the L form, especially the amino acids. Okay, now these amino acids which we're talking about, there's there's something that you need to understand. They are what we call essential amino acids and non-essential. So what are we talking about? Okay, so of the 20 amino acids, so others are essential, others are not essential. Now essential in this case, they're essential in the case that your body cannot make them. Okay, you have to get them from other sources, other foods that you're going to eat. Okay, so they are very much essential because your body can't make them. But the other ones are non-essential. Why? Because your body cannot make them. Okay, your body cannot make them, so I might say you don't need it because your body can already make it. But those ones that your body cannot make, they are really essential because your body can't make them. You have to search for them, probably in the food that you eat. Yes, like that. So you have to understand this concept. I've seen questions come on this, on this concept. Then another thing that you need to understand is, how do we classify these amino acids? So let's talk about classification of amino acids. So we said amino acids are classified based on what? On the R group. Okay, the R group, or the alkyl group, would determine the amino acid that you're going to have and its properties. So amino acids, they're going to be classified differently. Those which love water, anything that loves water is what? is hydrophilic, right? So it's water loving. So because it is water loving, so how can you classify in terms of classifications, in terms of two ways? We can talk about polar and non-polar. So other amino acids will be polar, other amino acids will be non-polar. Polar to mean they're able to dissolve in water. Non-polar, they can't dissolve in water. Okay. Then we can also classify them based on how they look, their structure. Okay. So others will be what we call aliphatic, and other amino acid will be what? Aromatic. Now aliphatic to mean they are straight, it's just a straight a straight protein. Okay. Aromatic to mean it's cyclic, it's in form of like it has a cycle. Okay. Let me say it has a cyclic compound. Okay. So you have to understand that. Then we can also classify proteins or amino acids in terms of their acidity. Okay. So based on is it acidic and basic. Okay. Then we can also classify amino acids based on if they contain sulfur. So we call those sulfur containing amino acids. So you have to understand these ones. Then classification number 5, we can also talk about what we call amino amino acids. Okay. Now here there is only one amino acid. Let me just mention it, but they won't examine you on this one. So the only amino acid is proline. Okay. Proline is really different from all the 20 that you're going to talk about here. Okay. So it doesn't fall in any of these classifications. Okay. So now what are we talking about? Let's talk about some of these maybe one by one, some of the amino acids one by one. Like glycine. Let's start with the first one, the simplest one, glycine. Now the formula for glycine, we said it is this is H. Okay, let me just write it a bit down. You got C, you got your carboxylic acid group, you've got your H, and you've got your H. So now is it going to be polar or non-polar? Looking at how the arrangement is. So polarity comes about because of sharing of electrons. So other elements are more electronegative than other elements. So when they form a compound, they tend to pull electrons towards themselves. Okay. So because of that property, what will happen is that one of the elements will be deficient, the other one will have a partial charge. So because of that charge difference, polarity tends to exist. You have the positive and the negative partial charges. Okay. So because of that, water can easily react with that compound to form other compounds. So those are polar molecules. So if you see a molecule that has this bond, like there's a lot of these CH bonds. So these CH bonds, if you look at the electronegativity of carbon, it is very small. Same with hydrogen, it's very small. So like they're close to each other, so like they'll just cancel out each other. So because of that, it will be a non-polar compound. So how are you determining? You look at your central carbon and your alkyl group. The alkyl group, we said this one is one that determines the structure and the characteristic of that protein. So this one is non-polar. Now if you look at the structure, is it aliphatic or is it aromatic? Does it have a ring, or is it cyclic? Okay, you're able to see that this one is it's just a straight structure, so it will be an aliphatic. It doesn't contain sulfur, acidity, and nothing like that. So let's talk about another one. Another one that we can talk about is alanine or alanine. So the structure for alanine would be H2NCCOOH. Okay, this is constant. What just changes is your R group, like we earlier said. So for alanine, it will have a methyl CH3. It will have a methyl R group or alkyl group. So now if you look at the compound, is it going to be polar or non-polar? So you're able to see that it also has a lot of C to C bonds, they will cancel, or C to H bonds, they will cancel. So because of that, this will also be a non-polar compound. Now is it aliphatic or aromatic? Does it have a ring? Is it cyclic? No. So this will be aliphatic. Okay, then let's talk about another one. Let's manipulate the same one. So the next one that follows is what? Valine or valine. Now valine, it will be CH, okay, connected to a methyl, to two methyl groups. Okay, so this group, as you are going to advance, as you are going to go more in organic chemistry, some of you, this is called an isopropyl. Okay, an isopropyl group. Okay, so now valine has an isopropyl group. Now is it going to be polar or non-polar? So look at it, there's a lot of CH bonds, so it will also be non-polar. Then you look at the structure, is it cyclic? No. So this is also aliphatic. Okay, then let's move to amino acid number 5. Now on amino acid number 5, this one is called leucine. So it's called leucine. Now leucine, it has the R group is an isobutyl. So this will be CH2, which will be connected to CH. This CH will be connected to two methyl groups. Okay, even on the other side, allow me to write it there, CH, like that. So this is called an this R group is called an isobutyl. Isobutyl because how many carbons does it have? One, it has 1, it has 2, it has 3, it has 4. Butyl just means that it has 3 carbon atoms. So this is leucine. Now is it going to be polar or non-polar? So you're able to see that even itself will also be non-polar. Look at the structure, it is also going to be aliphatic. It's just a straight chain. Okay, now let's talk about another compound. Let's say serine. Now serine, the structure for serine, it's just, let's say this is our CCOOH, this is our H, this is our H2N. The group that it has a CH2, then this is connected to an OH. Okay, so the CH2 is connected to an OH. Now look at the OH. Because of the OH, oxygen is more electronegative than these elements like carbon and hydrogen, so it will tend to pull electrons towards itself. So therefore this compound will be what? It will be polar, and we look at the structure, this is also aliphatic. It's just a straight a straight molecule. Then another compound that we can talk about is 309. Now 309, this is like C. So the function, let me just now start writing the R group. So this is the R group for 309 and CH3. Now we look at the molecules that are connected to this carbon. So we've got an oxygen here. We've got CH bonds, H bonds. So because of the oxygen, which is more electronegative, so this will also be what? To be polar. Is it aliphatic? Overwhelmingly true. It's aliphatic. It's a straight chain. Okay. Then let's also talk about another one. Now this is C. Okay. Then our R group for this one is it's CH2. Then this has this structure. Okay. Then this structure here on top, okay, I've lost my diagram. So we're saying it was CH2, this structure, okay, then on top this structure has an OH, okay, then this is connected to your carbon at the center. So look at the R group. So if you look at the R group, is it going to be polar or unpolar or non-polar? So you're able to see that there's an OH group, so this will be a polar compound. Then if you look at the structure of the R group, is it aliphatic or aromatic? So you're able to see that because it has a ring or a cyclic structure, this will be called an aromatic compound. This compound that we've drawn is called phenyl. Okay, phenylalanine. Okay, or alanine if you want, alanine. So this is phenylalanine. Then let's also talk about they've got other elements like tryptophan. Tryptophan also have like it will have CH2. This will be connected to a ring like that, and this ring it will have like two rings, okay, to like have two rings like that. So because of those two rings, this will be what? An aromatic. This is called tryptophan. So tryptophan is very, very important in terms of the skin and other things. You're going to learn about this protein as some of you will be doing medicine. So this is these are some of the amino acids that you need to understand, okay. Then I didn't talk about amino acids that are basic and sulfur containing. Now basics amino acids will just be those ones with the ones which are acidic or have COOH, right? This is acidic, okay. So an example that we can give is aspartic acids, all those kind of things. Then sulfur containing amino acids, one that comes to mind is methionine. Okay, you have to know methionine. Another one that you can talk about is cysteine. These ones are sulfur containing, so they will examine which of these amino acids is sulfur containing or does contain sulfur. So you have to know these two, okay. So now let's talk about we've said amino acids can be acidic and basic, okay. Now the ones which are acidic, now acidic, I've talked about aspartic acid. aspartic acid. Now I must make mention that so we've got an aspartic acid, and there's also what we call aspartate. So now what's the difference? Aspartic acid, which I'll not write the formula and stuff like that, or the structure. So aspartic acid, this one will be uncharged, meaning it doesn't have any charge, it won't do anything. But once you charge this aspartic acid, it becomes to be known, or to be called, you know, aspartate. So now it will be charged like that. So also have what we call, you know, glutamic acid. Glutamic acid, you know, when it becomes charged, it will be called glutamate. So you're going to learn about some of these things as you proceed. Then some of the basic amino acids that you can talk about, that I didn't talk about, you can talk about you know, histidine or histidine. You know, you can talk about arginine. You know, you can talk about lysine, you know, and many others like that. So the way I'm going to identify, you know, basic amino acid is because they will contain a lot of nitrogen compounds. Okay, like as long as you see there's some nitrogen in that compound, it will be basic. Okay, basic compounds. Then how do proteins form? So proteins form by what we call peptide bonds. Okay, this is just a bond between two amino acids. Now how does this peptide bond, you know, form? Okay, so two amino acids will come together to form, you know, probably a polymer, and that bond that, you know, joins these amino acid will be called a peptide bond. So let's draw two amino acids. Let's say this is our C. You've got our C. Okay, let me separate our OH to be like that. Okay, then you've got your R group, you've got your, you know, your hydrogen, and you've got your NH3 or NH2 actually. Okay, so like that, this is our first amino acid. So let's draw another one subsequent to this one. So this let me say, okay, allow me to do it like that. Then C, then this is an R group. Then we're saying this is your carboxylic group, like that. Okay, now how does a peptide bond form? So you are going to have the OH of one, you know, the OH of one amino acid combining with the hydrogen of another amino acid. Now when this forms, this, you know, this is water, right? So water will be released. So because water is released, what kind of a reaction is this one? This one is called a condensation reaction. Okay, some scholars will call it dehydration in the sense that you're losing water. So a molecule of water is going to be released when you're forming a you know, a peptide bond. Now when the peptide bond forms, now how is it now going to be? So allow me to wrap the part that has been lost. Okay, so this whole part is going to be lost as water. Okay, and a bond is going to be formed like that. Okay, so this is what we call a peptide bond. So look at the atoms that are involved in this, in the formation of this peptide bond. So the peptide bond is this one. Okay, so that will be your peptide bond. Now if a molecule has two, if it has two peptide bonds, it will be called the dipeptide. If you have three, tripeptide, and so on. Okay, so you have to know. But now if it has three, it will be called it. But now if it has 2 to 20, it will be called an oligopeptide. If this molecule has more than 20, it will be called now a what? A polypeptide. So you must also understand that one. So it's very, very important for you to know. Then proteins have got an important characteristic. They tend to form what we call, allow me to call them zwitterions. That's how when we used to go for jets, no one taught me this term, so when I saw it in one of the books, so for me I read it as zwitterions. Okay, so others, whatever you might call it zwitter ions, okay, or zwitterions, whatever resonates with you. So if we draw the structure of an amino acid, so we said amino acids, in the nature that you're going to, this is N, let me say H2 like that. You've got your carbon, you've got your you've got your H, you've got your R group, and you've got your carboxylic group like that. So this is the structure that I showed you. But now amino acids themselves, they don't exist in this structure. Okay, so that is not how they exist in nature. Okay, in structure I might draw them like that, but in nature they are quite like different. Okay, so the way it's going to be in nature, okay, this is your hydrogen, this is your R group, then you've got your H, your H. Okay, now instead of having an H here, this H will not be there. Why is it? Because an amino acid, because it has, we said it is an amino group and an acidic group. So because of that, it's going to react on itself. Okay, in nature it's going to react on itself. So when it reacts, this hydrogen is going to react there. Okay, then because it has reacting, because you've lost a proton, so because you've lost, let me say, you've got protons which are positively charged, you've got neutrons, you've got electrons which are negative charged, protons are positively charged. Now because you've lost a hydrogen is a proton. So because you've lost a proton, what will happen? You have excess of the electrons, so it means you have a negative charge here. So let me just write that. So because you've lost this hydrogen, since you've lost it, you have a negative, you have excess of electrons. But now this hydrogen has come to react here. So now on this element you have excess of protons. Okay, so it will be like that. Okay, so this is how proteins are going to act in nature. Okay, so so they'll both have they are going to exist both in the acidic form and in the basic form. Okay, now when you put this protein in an alkaline environment, okay, how is it going to look like? So in an alkaline environment, it will be a base, right? So the way it's just going to be is, okay, let's say this is our okay, why am I'm searching on this one? Because I've seen exam questions come on this this thing. So what are we talking about? If I'm going to put it in an alkaline environment, let's say in an environment where there is hydroxide. Hydroxide, you know, is a basic compound. Because of this, because I said the actual nature of these proteins or amino acids, they are going to exist in this form. So because they exist in this form and they have a charge, and I introduce let me say I introduce an OH, a hydroxide, a basic compound, what is going to happen is that one of the hydrogens will be grabbed, okay, and they'll make water. So because of that, this is the compound that we are going to have. So one of the hydrogen here is lost. So because it is lost, so this will be in an alkaline environment, okay. So in a basic environment, so in a basic environment, you are able to see that amino acids are negatively charged. Why? Because here they are both positive and negative, and because they are both positive and negative, we call them Zwitter ions. But now you put this amino acid in water or in a hydroxide solution. Because you put it in a hydroxide solution, the hydroxide solution will react with one of the hydrogens. When it reacts with one of the hydrogens, this positive will be neutralized. You only remain with a negative charge. Because of this negative charge, this will be, you know, in a basic on an alkaline environment, amino acids are negatively charged. Okay, so the opposite will be true. If you react this compound, if you react the Zwitter ion down with an acid, let me say an H plus, okay, an H plus. So what is going to happen? So your H plus is going to, you know, react with your oxygen there, and when it reacts with your oxygen, so this H plus is going to react with your oxygen there, and you know, you have H here, and the negative will go. So because the negative has gone, you only have a positive. So you are going to realize that in an acidic environment, amino acids will be positively charged. So they'll ask you questions on this diagram, so it's a must know. You must know that. Okay, then let's talk about the last part of proteins that you need to understand. You know, the levels of protein structure. Okay, levels. Okay, now we've got different levels of protein structure, and it's a must. You have to know these ones, very important. Now on this one, the clue that I'll give you here is on the level of structure. At least you must know that, you know, what that levels of structure is. You must know how to define it, and the other thing is you must be able to cite examples on each. That one will save you a lot in the exam, okay, because they'll ask you, you know, some, you know, examples of these, you know, structures. So the levels of, we start from the smallest one, or the primitive one, which we have what we call the primary structure. So, you know, just primary just means simplest. So this is just be a sequence, and a sequence of amino acids, okay. They'll just be arranged in a certain order, okay. So it's just a sequence of amino acids. The primary structure, okay. So what I mean is a sequence is just like a line, right? Okay, like let me say this is amino acid 1, it combines with amino acid 2, combines with amino acid 3, combines with amino acid D, you know, 4. This will just be a sequence like that, a straight chain like that. So this is the primary structure, okay. So here we're going to only have peptide bonds, okay, because you're able to see peptide bonds are just formed between, you know, two amino acids. So these are the common bonds that you're going to find in a primary structure. Then you can also talk about what we call a secondary structure. Now, in a secondary structure, these will be formed from peptide bonds. When now this, peptide bonds, these peptide bonds that are formed in a primary structure, when this one starts to call themselves up, okay, they'll form what we call secondary structures. Okay, so they can form to make what we call an alpha helix structure. They can also call to form what we call, a beta pleated sheet. Okay, are very important for you to know. Okay, so an example of an alpha helix that I can give, that they'll ask you in the exam on, is you have to know collagen, you have to know keratin. And keratin, where is keratin found? Keratin is found in your nails, in your hairs, in the beaks of birds. Okay, so the structure of an alpha helix, just to simplify it further, let me just do something like that. Okay, something like that. Okay, it has called itself. Okay, then for a beta pleated, maybe something like that. Okay, so an example of a beta pleated, you can talk about silk, you can talk about fibrion. Okay, so these are some of the things. Now, how many bonds is it going to have? Of course, it's going to have peptide bonds. A secondary structure is going to have peptide bonds. It's going to have hydrogen bonds. Then it's also going to have at least maybe one polypeptide. Okay, one polypeptide chain. Okay, then from secondary we have to also talk about what we call tertiary, the tertiary structure. Now, the tertiary structure, it's just the folding of those proteins that the secondary structure factors that proteins that we talked about. When those ones fold and fold and fold, they will form what we call, tertiary structures. And the common ones that you need to know is that some of them will be fibrous, others will be, globular. Now, fibrous, I can just say something, they look like lines, like that, like fibers. Okay, globular, something like looks like a circle. Okay, so something like that will be globular. So you have to know that. So an example of a fibrous, molecule that you can talk about is, collagen. Collagen tendons, stuff like that. Globular, we're talking about, an example a common example that I can give are enzymes. And you know that when you destroy the globular structure of enzymes, they get what? Denatured. Okay. Now, the most important form of collagen that they'll ask in the exam is the alpha helix, the secondary structure, not this one that we've given here. You're going to find that collagen, the one that is important to us, it is in the secondary structure, not in the tertiary. Okay, so they'll ask you that, so you have to know that. Then the bonds, you're going to have peptide bonds, of course, hydrogen bonds, but in addition to those ones, you're going to have what we call disulfide bonds. Okay, depends with the molecule. If it has sulfur, you are going to have what we call hydrophobic hydrophobic, you're going to have what we call van der Waal or van der Waals. These are just weak interactions that exist between molecules. In some compounds, tertiary compounds, you're also going to have ionic bonds. Okay, so these are some of the bonds that you're going to have. So why am I switching on bonds? Because I've seen questions come on bonds. Okay, let's talk about the last structure of proteins or level of protein structure. There's what is called quaternary structure. Now quaternary comes like something that has 4, right? Okay, so these will be large polypeptides that will be like joined like so much, and most of them they are in 4s. Okay, they're in group of 4s. So let me say something like this, let me say something like that. Okay, to be a big molecule, okay, maybe something like that, for 4 things. Okay, so examples of quaternary structures that you're going to talk about is hemoglobin. It's a common one. You can also talk about insulin. It's also a common one. That insulin regulates glucose, like we said, right? So an example that I can give for these ones, like if you look at hemoglobin, the structure of hemoglobin, just for context sake, I'm not saying you have to know hemoglobin. So as you're going to cross, some of you, hemoglobin in medicine, you're going to talk about it having 4 chains. In biochemistry, okay, it will have 4 chains. These 4 chains, you have 2 alpha chains and you have 2 beta chains. Okay, so that's how you're going to go. Then these alpha chains, the alpha chains have got 141 amino acids. The beta chains have got 146 amino acids. So these are big molecules. Okay, that's what I'm talking about. Then if you look at the structure of insulin, we're not talking about structures of insulin here where you're supposed to master. No, just for context sake. So insulin, there'll be zinc. Most of the people who have like insulin problems, they give them like zinc molecules and stuff like that. So this zinc will be connected to a lot of molecules. The zinc in the middle, you remember these ones, we call them what in chemistry? Coordinate compounds. Now coordinate compounds to mean they are complex. They're also called complex compounds. How are they complex? Because they are connected to ligands. In chemistry, we call these ones the ones that connect to the metallic element that is on the middle. Okay, these ones are called ligands. Okay, so ligands, what they'll be doing, or ligands if you want, they'll be donating electrons to the central atom. So these are big molecules that we're talking about. So that's like insulin. Okay, so I think this is all that you need to know about proteins, and just some questions on proteins. So this is where we're going to end for today. See you in the next session.